Good morning, everybody. We'd like to start off by doing a quick sound check. If you could please confirm that you can hear us clearly in the questions tab by just typing in yes. Once we see a few answers come in, we'll get started. Okay, great. We got some confirmation. Here we go. Hello and welcome, everybody. Thank you for joining us today. My name is Patrick Moran. I'm on the marketing team here at H2O.ai. I'd love to start off by introducing our speakers. Vinod Iyengar comes with over 7 years of marketing and data science experience in multiple startups. He brings a strong analytical side and a metrics-driven approach to marketing. And when he's not busy hacking, Vinod loves painting and reading, and he's a huge foodie and will eat anything that doesn't crawl, swim, or move. Now, Bojan Tungas was born in Sarajevo, Bosnia and Herzegovina, and having fled to Croatia during the war, Bojan came to the U.S. as a high school exchange student to realize his dream of studying physics. A few years ago, he stumbled upon the wonderful world of data science and machine learning and feels like he discovered a second vocation in life. And some of you may know Bojan through his Kaggle competitions and his Grandmaster title. Now, before I hand it over to Bojan and Vinod, I'd like to go over a few webinar logistics. Please feel free to send us your questions throughout the session via the questions tab, and we'll be happy to answer them towards the end of the webinar. And secondly, this webinar is being recorded. A copy of the webinar recording and slide deck will be available after the presentation is over. Now, without further ado, I'd like to hand it over to Vinod.
Thank you, Patrick. Thank you, everyone, for joining us today for this really fun discussion, I hope. And I'm really excited to do this webinar with Bojan, who's one of our amazing Kaggle Grandmasters. And actually, as the title slide points out, he's a double Grandmaster, which is a very, very unique thing. I'll let Bojan explain what that means in a bit. But before we get started, a quick sort of intro about who we are. For folks who don't know about H2O, we are an open source machine learning company, been in business for about 7 years now. We have a really large data science community, so nearly 200,000 data scientists, close to 15,000 companies using us on a regular basis, and a lot of the, close to half of the Fortune 500 companies are also using H2O on a regular basis. We have a huge meetup community, 100,000 plus meetup members meeting regularly in different cities around the world. We have a meetup, I think, pretty much every week there is a meetup, H2O meetup in some part of the world. So if you're interested, do feel free to join the community and learn more about data science. From a product perspective, we have, these are the products that most of the community knows us for. On the left, you have our open source products, H2O Open Core, which is 100% open source, provides in-memory distributed machine learning with all the popular algorithms that are very commonly used by data scientists. Water, that's H2O running on top of Apache Spark. Again, very popular, probably the best machine learning on Spark, as we like to think of it, and our customers validate it. So nearly a third of our open source community uses us through Sparkling Water. And then we ported some of these algorithms to be accelerated on GPUs and created a product called H2O for GPU that gives you algorithms like Gradient Booster Tree, GLM, Random Forest, PCA, etc., fully accelerated on GPUs so that you can take advantage of the latest and greatest hardware out there. And finally, Driverless AI is our commercial automatic machine learning platform. That's sort of the fastest growing platform in the space right now. We automate the entire machine learning workflow from data ingest all the way to production. We'll talk more about that later in the session. But that's extremely popular, built for data scientists, built by the Grandmasters, including Bojan, and it does some really cool stuff. With that, let's jump into today's topic. Quick. So why AutoML? So this is a quote from Gartner, one of the reports, and this is no news to anyone who's in the industry, right? So there's a deep shortage of data scientists and ML experts, and it's not likely to improve in the short term, right? So short to medium term, because the schools, the colleges where folks are coming in, they are only beginning to adapt now to for the latest techniques. Another challenge with that is that the space is evolving so fast that even when a technique or a set of frameworks are popular today, they may not be popular in a year or 2 years down the line. So you need to constantly adapt, and that makes it really challenging for creating a corpus of or a pool of experienced data scientists who can keep coming in. And that's a big challenge for enterprises too. So the goal is, can we use AI to build models and help increase the productivity of employees in different enterprises to do this? And that's I wanted to put this cartoon up. One of my colleagues showed it, but the challenge, of course, is with AutoML is that when you show something like AutoML to data scientists who are busy coding and cracking away, they're too busy to try out something new. And that's why we want to sort of first spend a little bit of time understanding what AutoML is, what the state of the art is, the spaces, and Boyan will sort of and he has a really good sort of understanding of framework for looking at where AutoML is as a space. And then look at what are the top considerations if you are an enterprise or a data scientist, even if you want to pick an AutoML platform for your company, what should you be looking at? With that, I'm going to hand it over to Boyan over here to let him take control and talk about the data science workflow and sort of the 6 levels of AutoML. Over to you, Boyan.
Thank you, Vinod. Good afternoon or good morning, everyone, depending which time zone you are in. As they mentioned, my name is Boyan Tungus. I'm a Kaggle Grandmaster and a Senior Data Scientist at H2O. This presentation has been adapted from a presentation I gave a few months ago at Kaggle Days. And there I want to kind of take more of a kind of bird's eye view of what machine learning is, what data science is, and how can we automate machine learning and take it from there and understand like what different degrees of automation in machine learning may mean. Here we have a general kind of data science workflow that goes from formulating the problems, acquiring data, to data processing, modeling, deployment, and then monitoring. Many of these stages are actually included in our driverless AI tools. But for purposes of this kind of bird's eye presentation, I will just concentrate on the middle part, on this modeling part. So the modeling is part where you actually have all the data in more or less the shape that you want it to be, and you're just having to kind of create the best, most effective model that you can. So now, what the best model is will depend on different situations and different domains. Many times it means just getting the most accurate model, but in many other situations means like most robust or some other thing that needs to be optimized. But to actually go beyond that, I want to kind of start and kind of make why would anyone want to kind of have AutoML? So like AutoML, there are many reasons. As Vinod has already mentioned, there's increased demand for data sciences and machine learning applications, demand that's not always being met. There's a relative shortage of people with relevant skills, and the number of positions is far outstripping number of degrees or any kind of certificates that's being offered in the field. Sometimes you just want to try ML on some simple use case before committing to actually having a data scientist. Yet you want to have it have ML that's as good as, or at least close to being as good as something that a data scientist would produce. So you want to kind of try the waters before you swim in. And then various non-machine learning practitioners, analysts, marketers, IT staff, they want to have some part of their workflow that includes machine learning, but they don't really necessarily need to have a full-time data scientist. So a tool that would do most of the things that the data scientist who creates machine learning models would do would be useful for them. And then you know, if the tool is good enough and pretty much does everything that you really need it to do, then you can save a lot of money. Instead of hiring a data scientist for I don't know, $150,000 a year, you can get a tool that's much cheaper than that, and then use it on a need-to-need basis only when you actually really need, and get most out of the investment. Another one is faster iteration. If you have a tool that actually can do automation and machine learning, it allows you to faster iterate over development. Instead of having to code something and take a few days to actually implement in the code, you can actually just take the data, put it inside of a pipeline, and within a few hours you can actually have an answer to your question, or see whether the data that you have can actually answer those kind of questions. And this is one of my favorites. If you perform more and more different experiments, you're getting closer to actually really formulating the problem and approaching machine learning problems as a scientist, meaning running experiments, looking at the outcomes, and making your decisions and a future iteration based on those decisions. So like, this is one of my mantras, putting science back into data science. And then one of the things is the number of people who are entering the data science field is increasing. And you know, there's a competition for these jobs. This is actually my son a few months ago. He picked up a book on neural networks, and I don't know how much he's retained, but it's a direction where we're headed with data science. So these 6 levels of AutoML, I was inspired by, if you might be familiar with 6 levels of autonomy in driverless cars. So there are different levels. We are pretty much at the level 3 or 4 with driverless cars, depending who you ask. Fully autonomous cars would actually just kind of pick you up from spot A, take you to spot B, without actually really needing to give any additional guidance. So I wanted to come up with something similar for automated ML and come up with 6 different levels. So naturally, the first level would be level 0, which is no automation. You just code stuff from scratch, and probably one of the relatively low-level programming languages like C++. And one person who does that to this day is this Austrian grandmaster, Michael Jarer, who I had the privilege of working with. And looking at his code is just breathtakingly detailed and sophisticated, but obviously not most people cannot really implement something like that. Level 2 would be just use of some high-level algorithmic APIs like sklearn, Keras, Pandas, H2O, XGBoost, and similar. So that's where most people who are participating on Kaggle these days, that's where they are. We all rely on some of these tools, and probably the reason that Kaggle has expanded and become so prevalent and popular over the last few years can be easily tracked to like promotion of some of these tools, some of which were actually first introduced on Kaggle. So Keras and XGBoost were actually specifically introduced for Kaggle competitions. Now that they've become standards for a lot of machine learning workflow. Now, level 2 is you automatically tune a hyperparameter and do some assembling and some basic model selection. There are several packages that are similarly high level, like sklearn, that help you optimize hyperparameter. There's a Bayesian optimization, which is a very popular package, is the one that I like the most. HyperOpt is another one. So there are several different strategies, and many of them are getting automated nowadays for tuning hyperparameters for some of these algorithms. And there's assembling is sort of the golden standard these days for making the best and most predictive models. We all know that no single model can really outperform ensemble of different models that each have their own strengths and peculiarities. So some of the level 2 automatic machine learning tools can do these assemblings by themselves. And H2O package, AutoML is one of them, for instance. It can build several different models, XGBoost, generalized linear model, and a few others, and then assemble them into like a very strong predictive model. Now, level 3 is more or less where we are at right now as an industry standard, or maybe a little bit of level 4. This is where automatic technical feature engineering comes into place, and by that I mean feature engineering that can be done just using features, technical aspects of the features without really understanding the domain where these features are coming from. That would be like label encoding for categorical features, target encoding in some cases, binning of different features and things like that. So these are technical things that don't really depend by and large on expertise in a particular domain, that they can be automated, and that's where we are right now. Another one is the introduction of graphical user interface, which I think really liberates machine learning from being just a toolkit of software engineers and data scientists to becoming much more accessible to a really wide spectrum of people who want to use it for their daily work. Now, if you have some kind of very specific domain, they have a certain feature engineering would only make sense there. So, for instance, in a credit risk, loan per income would be a very good feature that otherwise you may not be able to figure out if you're just looking at anonymous features. So this would be an example of some domain-specific feature engineering. Data augmentation is, again, using different, this is more the domain-specific data augmentation. Interesting example of that was recently that I came across a presentation where, in order to classify images for different eras, artifacts would be added to those images that would only be relevant to that era. So like if you have a 1950s image and you add a radio from that era, that could be okay. But if you add an iPhone to that, that would actually be a really bad idea. So that would be some domain-specific data augmentation. Now, for level 5, which is the 6th level in this taxonomy, that would be full machine learning automation. It's the ability to come up with a superhuman strategies for solving hard machine learning problems without any input or guidance. And then possibly having fully conversational interaction with a human user. So something that, instead of talking to a data scientist, you could talk to automation machine learning tool and come up with a strategy of how best to formulate a problem and what kind of model to create. Now, we are still pretty far away, even kind of thinking about this stuff. Many people have told me that it sounds more like science fiction than science reality. So the big question is full AutoML, I should say, even possible? According to the free lunch theorem, there is no single approach to any machine learning problem that will outperform all the others. However, we're not really trying to solve any possible, in the universe of possible machine learning problem, but something that's very relevant to real world, which greatly simplifies and restricts the number of problems that we can solve. And for real world problems, we do have people who have expertise in different fields who can actually come up with strategies that we can learn from those. I came up with this term Kaggle optimal solutions, and that would be the best solution that could be obtained through Kaggle competition, provided there are no leaks, special circumstances, and other exogenous limitations. So Kaggle has been proven to be able to outperform a lot of times even the best domain experts in particular fields in coming up with solutions. So this would be some kind of superhuman possibility. So if you have enough people working on a problem for an extended period of time who are familiar with machine learning tools, they can come up with optimal solutions that in many ways no single human could possibly come up with. Now, we know that these solutions do exist because there are Kaggle competitions, and I'm kind of claiming that this would be, if we can capture this, that would be something that a fully automated machine learning environment could do. And superhuman AutoML would beat best Kaggle almost every time, and that would be something that's still far ahead and not really clear how can we get to that point. So I'll just briefly again go over some of these levels. So no automation, you implement machine learning algorithms from scratch. It requires very high level of software engineering, and it's not easy to actually do for most practitioners of data science. Now, at this level, in the old days, most of the people who were doing machine learning would actually be writing the tools from scratch, which obviously not optimal use of their time. And it's very, very hard to scale. Now, so this is I'm just giving a logistic regression as implemented in C++, and I'm not sure if you can actually really see it, but it's really a bear of implementation. And this is my very crude depiction of what making those tools look like back in the days when we were doing it from scratch. Now, there are times where you do want to do something from scratch, namely when you really want to understand some of these algorithms, and there's some good resources out there, including this book that I highly recommend, where you do implement some of these algorithms from scratch. If you've been a data scientist for a few years and already have some familiarity with all these algorithms, it would behoove you to kind of take a look and really try to understand and try to implement some of them from scratch. Obviously, you can't do fully some of these more complicated residual neural networks from scratch. That would be impossible, but some of the simpler algorithms would definitely be worth your time from an educational perspective to try to do. So now we live in days where there's a really plethora of different APIs to use for building machine learning algorithms, data science pipelines, and if you're into that stuff, then this is really a great place to be. But the problem with this is, like, pretty much every day, if not several times a day, I hear about a new great tool that's being implemented that really does part of your data science workflow, and it's very hard to keep track of all of these things. So it's great from a standpoint that many of these can do a lot of things, but it's still very hard to kind of keep track of all the tools that are out there. So high-level APIs, as I mentioned, like sklearn, pandas, XGBoost, Keras, H2O. It allows for novices who still have some coding skills to actually go from building very simple models to being very proficient in a very short amount of time. It's pretty standardized. For instance, sklearn API is becoming sort of the default these days. And here, for instance, is sklearn implementation of logistic regression. If you remember that slide from a few slides back where it was implemented in C++, you can immediately see why having these APIs would really make life so much easier for most practicing data scientists. So for level 2, we have automatic tuning. You could consider it first real AutoML. It's where you start taking several different models, take a data set, specify a target, and let it create best algorithms out of some subset of algorithms that you can think of. It selects, validation strategy, cross-validation versus time validation split. Now, this is still very, in most cases, this automatic cross-validation works, but really hard cases are the ones where there's some peculiarities of the data, and simple out-of-time validation or CV validation can actually really burn you. So this is one of those things where you really need to know that your data is such that some of these cross-validation strategies can work out of the box. And then it optimizes hyperparameters. It chooses the best learning rate, for instance, number of trees, subsampling of your data set. So these are all hyperparameters that many of these APIs let you pick, but it's very hard to come up to understand which ones are the optimal for given problem. And then it performs basic ensembling. For instance, if you have two algorithms and they give you predictions, you can take average of those two predictions, and that's very simple ensembling. But if one is performing much better than the other one, yet the other one is not completely useless, finding the right kind of weights, it can be tricky. And some of these automatic tools do that for you. So for instance, hyperparameter optimization level 2 there's several approaches to it. There's grid search, where you choose pretty much all the available hyperparameters in some space and then try every one of them, and that's very computationally expensive. Random search, where you just do subset of those hyperparameters, and this is the comparison between the two. And then there's Bayesian search, which uses Bayes' theorem to actually do something very smart about where to look for next potential hyperparameters given the one that you already looked at. And it uses Gaussian process to actually look for different potential hyperparameters. For ensembling, some of these level 1, quote unquote, algorithms are already considered ensembles, like random forest or XGBoost. But for all practical purposes, as practicing data scientists, we treat them as algorithms, as a fundamental algorithm that we want to ensemble with some other ones. So we want to take a look, for instance, different approaches to assembling, like blending, which is what I mentioned earlier, finding weights of average of weak models, boosting, which is iteratively improving blending, and there's stacking, where you create k-fold predictions of base models and use those predictions as meta features for your next level model. So these are some of the basic assembling approaches. And most of the level 2 algorithms and level 2 AutoML solutions can do a pretty good job with these. Okay, so for instance, this is an example of a very complicated ensemble where you assemble things at several different levels for a final prediction. And this particular example is for my solution for distinguishing between cats and dogs. Now, you would think that this is one of the simplest possible problems, at least when visualization. You can do some very fancy and very complicated involved assembling, and some of the more advanced machine learning tools can do this for you. Now, for level 3, which is where most of the good solutions on the market are right now, we have automatic technical feature engineering and feature selection. So feature engineering refers to the fact that you create new features or you do something to existing features to make them yield more information. There are many ways of doing it. I mentioned some of them: binning, finding feature interactions, target encoding. Many of these are implemented in good AutoML solutions. Technical feature selection is a little bit harder to do, and it's not very well done even by most experienced machine learning practitioners. That requires, once you create many of these new features, which ones to use. Even the ones that you already have, many of them may not be optimal for your problem. So you have some tool that automatically decides which features of the ones that you created to use would be good for the model. And then technical data augmentation is where you, for instance, for images, you can flip, rotate, add some noise, and do that other things. And finally, we have graphical user interface, which makes non-technical people be much more effective with creating good machine learning models that they can use for their own workflow. And example analogy I would like to do is if you have word processing versus typesetting everything in LaTeX, this makes more people be able to write very good looking and effective documents, even though they don't have any particular low-level technical skills. So here's automatic feature engineering. You can use different coding for categorical data. You can use different codings of numerical data, aggregations, and feature interactions. So these are all things that they can do, you can do with tabular data. Now, word embedding is when you have textual data and you actually turn text into some kind of vector in some vector space. And then for images, you can have pre-trained neural networks that can actually turn image into, again, array that you can then use for other machine learning algorithms. And now for technical feature selection, we have things like selecting features based on feature importance in some test model. You train a model, see which features are most relevant, and then just keep top, 5 of those. You have things like forward feature selection, where you select feature, see how it performs, add another feature, see if the model improves, then keep that feature, and if it doesn't, throw it away. So go one by one through all the features until you find a set that really works well with your given model. The opposite is recursive feature elimination, where you actually start with all the features you have and then eliminate one by one all of them. Now, all of these are very computationally intensive and not maybe optimal for most problems, especially if number of features easily can go into thousands of tens of thousands after some of the feature engineering. There's also permutation impact, where you just take one feature out at a time and see how it works without that feature. So as I mentioned before, generating new features, results in combinatorial exposure of possible features, and we need some more sophisticated strategies to actually select features that would be useful for our model. And this is what some of the best AutoML tools that are on market right now can do for you. For instance, one of the approaches for this is genetic programming, where you evolve, quote unquote, features, and then look at which ones survive and create a new subset of features based on those evolutionary algorithms. And that's something that's, for instance, implemented in H2O's driverless AI. Now, when it comes to technical data augmentation, there are many different things that you can do. For instance, adding stock value prices to temporal data. If you want to look at how economy is performing, or some other financial indicator is performing well, you can look at add stock prices over time to see if there's some correlation between stock market and default rates for some kind of loan. You can add geographical information. This is something that's very informative, but with this one, you have to be very careful that you don't introduce some kind of regional biases in your models, which for regulatory purposes can be a questionable practice. And for instance, FICO scores can be another important additional piece of information if you're running a loan business. FICO scores obviously would be a great piece of information to have. Then there's this trick that some of our teams on Kaggle competitions have discovered, where you have textual data and you do some kind of automated translation of the text into another language and then translating back in the original language. That introduced some noise, and the hope is that this noise would actually help you with ensemble of the model that you're building. And again, this is very technically straightforward. There's no human in the loop in this process, and no understanding of either one of the languages needs to be involved. Then injecting noise is a tried and tested way of dealing with data augmentation. And then you can do various math transformations, sound and images and other things. Then there is image-specific transformation, blurring, brightening, color, saturation, etc. So there are a lot of different ways that technical data augmentation can be done. There are libraries out there that do it for you, but there are good solutions, AutoML solutions that also do it in the background. GUI is, again, one of the things that I think every level 3 AutoML needs to have. It facilitates interaction with software, allows for many non-technical people to use it, and further facilitates iteration and development. Now, level 4 is beyond where we are right now. It requires automating specific feature engineering. It requires ability to combine several different data sources into a single one suitable for ML exploration. So if you have, again, I like going back to the loan business problem. If you have different tables that come from a different aspects of the loan process, how you combine these tables into a single one that can be suitable for machine learning is non-trivial. How do you aggregate data from a transaction history or whatnot? None of these things are easy to do, and we don't have automated way of doing it to this day. Some domain-specific cases may have it, but in general, we don't have automatic feature generation. You can do some advanced hyperparameter tuning where you go beyond Bayesian optimization and some of those things that we mentioned before. Automated domain problem-specific feature engineering where you do aggregations according to what makes sense, for instance, for your problem. Adding particular kind of noise to images that really make sense for those kind of images and no others. So these are to this day, require a lot of human interaction, human understanding of the problem. Then ability to combine several different data sources, joining tables, understanding which merges make sense and executing them, understanding which aggregations make sense. So all these things still require a lot of human interaction. Advanced hyperparameter tuning. Manual hyperparameter tuning is still my #1 go-to approach for tuning hyperparameters. I've tried many of these packages, and I can still, by using my own intuition and experience with tuning some of these XGBoost, for instance, algorithms, I can still come up with a better hyperparameters than any of these auto solutions out there. So there's still a lot of intuition and human understanding of that's involved that we still are not able to completely capture. So, this is a deep understanding of the data. It may require some transfer learning. So building hyperparameters based on the previous experience with different hyperparameters. So for specific feature engineering, so domain understanding will be crucial to create different features. Ability to get additional data based on a problem and domain and integrate into the ML pipeline. That's still very much where real-world data scientists come into play. And now we're going to full ML automation. This is a little bit beyond what even we are able to kind of foresee right now. But this is, I feel, what fully automated machine learning solution would look like. It requires ability to come up with superhuman strategies for solving hard ML problems without any input or guidance. fully conversational interaction with a human user. So this would be essentially having a Kaggle Grandmaster sitting in front of you and solutions to your problem. So up to level 4, all of the automation is essentially hard-coded. So it's still something that you have to come up with prior to deploying the solution and then having the solution run itself. But now for full automation, we need to use machine learning approach to how to build it. And what that means is use machine learning to teach AutoML systems how to do machine learning. So machine learning is approach to building software and products that requires a lot of data. Now, we would really require a lot of data and use cases of how to build machine learning pipelines and then train the model on all of them to actually come up with a better superhuman approach. We might need some unsupervised approach. So this would be machine learning for machine learning for machine learning. So the idea in principle is simple. Give the ML system a large collection of ML problems and their solution, and then let it learn how to build ML systems. Now, idea is simple, execution is hard because we still have relatively few machine learning problems to work with. It's very daunting. Even the simplest ML problem requires thousands of instances to train on for decent performance. However, we probably don't need to build all this from scratch. We might be able to bootstrap on top of the previous level of automation. So if you have all these previous levels and it's working fine, then you can do something maybe like reinforcement learning. Or you can use unsupervised techniques. If we can parameterize our problems and parameterize possible solutions to them, then we can come up with a space or universe of human relevant ML problems. We might be able to find some patterns in there. So unsupervised methods are much better suited for situations where you don't have too much data, but you still want to understand something about it and come up with solutions. And then there's reinforcement learning. Building ML solutions and based on how well they perform, adjust the architecture. So this would be, have an environment where machine learning tools can actually learn from the experience of trying to solve machine learning problems. So this would be adversarial AutoML. Have AutoML systems compete against each other, make a Kaggle competition that's only open to AutoML systems and iterate. So this is a possible something that could come in the future where you have different AutoML systems compete each other and learn from the experience. And I would argue that fully conversational interaction with human user would be another thing that you would need from such a system. So again, it wouldn't, it would be an AutoML system that doesn't necessarily pass the full Turing test, but has enough of a domain-specific understanding of machine learning that can pass Turing tests for machine learning problems and be able to interact with you like you would with any other data scientist. It would democratize machine learning and make it even more accessible than it is right now. And it would, a lot of times, even formulating a machine learning problem is a very iterative process where you interact with people, domain experts, other data scientists, analysts, to actually come up with something that's really can be really useful for everyone. And actually, there are a few downsides, but I'm not going to spend too much time on these. I'm just going to click through them because I want to hand it over to Vinod, who will introduce you a little bit more to our driverless AI system. All right.
Thank you, Boyan. This is extremely useful to understand where the state of the space is, right? So in a nutshell, sort of to recap what Boyan said, I think of them almost like Gen 1, which is basically a lot of the open source frameworks which do hyperparameter tuning, ensembling, and sort of leaderboard sort of approach. Then you have Gen 2, which Boyan talked about, just kind of level 3 and level 4, where you're getting to feature engineering, evolutionary, genetic algorithm type techniques to do a lot of the work. And then going forward to like Gen 3, which is basically kind of like getting to full AutoML, where AI is available sort of at your fingertips, as you're looking at data. So it's using new interfaces too, like in different places. Now, with that said, if you're an organization or a data scientist looking to pick a platform to do AutoML, what should you be looking at today? So based on what the state of the industry is, here are the top considerations in my mind. So to begin with, think of, hey, how can you automate the entire workflow? So I know Boyan mentioned this earlier, where we especially talk about the feature engineering and modeling, but essentially if you think the entire workflow is data prep, data ingest, and at the downstream you have model deployment monitoring. So how can your platform sort of automate as much as possible so that you can spend more time thinking about the problem framing and actually evaluating if it's doing the right thing? Look at portability and flexibility becomes important. We'll spend a little bit more time thinking about it, but what that means is you don't want to be locked into one vendor or one environment. So there are considerations around where the data is. Is it on cloud, on-prem? Where is the compute running? What about running it in different sort of hardwares like GPUs or using GPUs or CPUs or the latest processors for that matter, and then running them in sort of different configurations as well. Along with that, it also comes the idea of extensibility. So till now, we've been thinking about automation, but as I mentioned, you're never going to get to full automation, really. So in the interim, can you extend it? Can you customize the platform, add your own sort of flavor to it? So these could be or these could be new algorithms that the platform may not have today, but other ways to add those. So that's an important consideration. And finally, explainability, trust, and transparency. That becomes really important. With automation, it becomes even more critical because essentially now you kind of have a master black box. So if you think the algorithms are black boxes themselves, now you have a master black box, which does AutoML. You go give it data, and it gives you a model and a prediction. So if you can't explain and validate the model, then that becomes a big challenge. So thinking about what tools are available to achieve that is a big consideration when you're picking a platform. And then you also want future proofing, right? So part of the reason why you're doing AutoML is as one person cannot learn everything or be able and master in everything, and it goes back to the no free lunch theorem. I have my own take on it. There's a no free lunch theorem for data scientists as well. No one data scientist is an expert in every single field. Like even in Kaggle, we have some folks who are deep learning experts, some folks who are GBM experts, some folks who focus on feature engineering, right? So you want the tool or the platform to do all of it for you and find the latest and greatest in every single field. So think about that becomes critical. So just to extend that a little bit further, right? So when you look at the challenges in the AI model development workflow, and there is feature engineering, model building, and model deployment at a high level, but even within those, there are sections, right? Looking at things like simple encoding, advanced encoding, feature engineering, feature generation, which is looking at interaction effects or transformations. And then within the model building part of itself, you have the algorithm selection, what framework to use, tuning of the parameters, and then ensembling that Boyan touched upon quite a bit. And then when it comes to deployment, you are looking at can you generate a pipeline? Can you easily deploy it? Can you monitor it? Can you explain the results and then document the whole workflow? And all of these are time-consuming tasks because each of them require a lot of work. They're often iterative, and you have to often hand-code them. So look at tools that can sort of automate the entire workflow. And at H2O, for example, we have two AutoML sort of offerings. One is the H2O open source AutoML that's very widely used, and that basically focuses on the model building part, right? So it automates the model building part thoroughly. So it does all the algorithm selection for you, the parameter tuning, and then the ensembling. But it also does some simple encoding and generates a pipeline, at least for the model building portion. And then when you jump over to H2O driverless AI, what we set out to do is solve as much as possible for the entire workflow, right? So we took the remaining pieces as well and automated it. So that becomes useful for you to see when you're picking a platform. Now coming to the portability and flexibility question, as I mentioned earlier, you're really looking at saying that, hey, can your platform run on cloud? Can your platform run on in a hybrid fashion, on-prem, and what are the considerations when you're doing that in a different way. So, for example, if you want, as your data size increases, you want the ability to run it in a distributed fashion, the ability to handle larger data sets, handle varied data sets, for example, and those become critical. For example, data sources could be coming from whole different places, right? So you cannot restrict yourself to one single data source. It could be coming from on-prem or cloud, and then integrations, because there's a whole bunch of tools in the arena that you probably are going to be needing to use along with your AutoML platform. So think about picking platforms which can integrate as much as possible with other tools. So if you already have certain set of tools for data munging, for example, data prep, or even for infrastructure management, the ability to integrate with existing frameworks and platforms is critical. In the same breath, also think about all the different data sources that your data might be coming in, right? So you cannot just have the simple CSVs or the TSVs, but there's big data formats, there is data frameworks, data frames which are coming from different platforms. You want the ability, you want a breadth of connectors and ingestion sources. So what does this look like? So these are some examples that we published ourselves with some of our partners, right? So when you talk about flexibility, so this is a cloud deployment that a lot of our customers do. So data coming in from Snowflake and other data warehouses on the cloud, pulled in through Alteryx to do the data prep, and then driverless AI for the feature-changing and model building. And all of this running on either AWS or Azure or GCP. This is just one deployment reference architecture that's very popular with our customers. But very similar to that, we can do a hybrid one. And again, instead of running through cloud-wide data warehouses, you're running it on something like Blue Data, which in turn connects to on-prem HDFS, but also blob storages. Again, using some data prep tool in between, and then running this, running the feature engineering and machine learning in driverless AI. So the environments you run are going to be very different. And if I flip this to a completely on-prem based solution, now you're looking at data integration from a whole bunch of data sources like SQL data warehouses or HDFS or just file systems like Menu, and pulling that in to do the data quality transformation in something like Spark, for example, and then running the feature engineering and model building in driverless AI. So you want the platform to be flexible across all these sort of different type of deployments. And as you're considering that, think about these things, right? Like data gravity becomes critical. As your data size gets larger and larger, you don't really want to ship it across. So find a platform that can run close to your data, right? So if you can, you can avoid shipping the data over the network. It also makes for a lot of sort of like a very secure connection in the sense that oftentimes some of these data might have private data, PII information, or HIPAA compliant data, in which case you don't want them to be sent to different places without a lot of careful vetting. So if everything can run in your own secure firewall VPC, then it's perfect. Similarly, look at frameworks. So there's no single sort of tool or solution, and this space is rapidly evolving too. So you need to know what you don't know, right? Like having an awareness of what you're not good at is important, so that you can have the platform find the best ideas for you. So the latest technologies, latest techniques, new networks, new architectures. Can you be the first to market? So pick a platform that can give you the velocity of innovation and implement that for your company. Then finally, similarly in the same breath, you have hardware too. So there's a lot of improvements and progress happening on the hardware front. The latest CPUs and GPUs are much faster than even like a couple of years ago. And especially when it comes to AutoML, it is a very compute intensive or resource intensive operation. So you do want to take advantage of the latest innovations there. So find platforms that can take advantage of like the latest A6 GPUs or FPGAs for that matter, whatever you can, right? So that becomes critical. And this is just an example of how, like for example, driverless AI, we are able to run this on completely different configurations using, say, like something like Optane DC memory, persistent memory from Intel with DRAM, with a very heavily overloaded sort of persistent memory and the latest CPU infrastructure. And conversely, on the other side, with the latest sort of DGX1 and DGX2, we can run on GPUs as well. So up to 16 GPUs scaled on a single machine with 32 gigs of GPU memory each can give you some phenomenal performance as well. So we can find platforms that can take advantage of the latest hardware. Right? So this is a couple of good examples over here. Let's talk about extensibility for a second. What I mean by that is, as I mentioned earlier, so you want, at least we think of it this in three different ways, right? So first is, even if your platform does some automatic feature engineering, what about other stuff that you know as a domain expert? Can you bring those in? So custom feature engineering is important, right? Doing your own transformations, your own domain-specific interactions, for example, bringing them into the platform. Can the platform take advantage of them? Custom algorithms. Obviously, there's a whole bunch of different frameworks out there which are really good at certain a bunch of different problems, but there's new stuff all the time. So you want to be able to try new stuff and see quickly if that makes sense for you. So having the ability to bring custom ML algorithms is critical. And finally, custom loss functions. So this is a part which is going to be very tough to automate anyways, right? This is the part that you know very well. So you know what your customer's lifetime value is. So a churn of a highly valued customer as compared to a not so valuable customer is very different. So you want your loss function to be optimized for that. You want their to optimize for business metrics that are important for you. So can your platform find a platform that allows you to do that? And in driverless AI, for example, we have now the ability to add custom transformers. Literally, you can bring in your own Python code, simple Python recipe that can do this for you. And it's just one way of doing it. And we are using a very simple scikit-learn style API, so any data scientist can implement their own transformer or their own custom model. And then driverless AI's engine will use them just as if they were native. So that's important. But along with that, look for platforms that give you a whole community of open source recipes, right? So you don't, oftentimes you'll find is that you'll want to use recipes that are already pre-built. So find a platform that has a pre-built community, because then you can reuse and repurpose, and there's a lot of collaboration that happens. Things get better. So instead of just picking a platform that does all the work themselves, obviously no company can add so many people. The community is obviously larger, and especially if you can take advantage of the Kaggle community, which has some phenomenal scripts and recipes. Can you bring them into your platform? So the final topic I want to touch on very quickly in only a few minutes is about explainability. So trust, transparency, and explainability, they're critical. Why do they matter, right? So obviously, as you're doing, AutoML takes into the black box realm a little bit, right? So because you're letting the machine make all the choices, the parameters, the features, the tuning, and it's even the algorithms, right? So everything is being done by the machine. So you essentially have a bigger black box now, and you have to sort of figure out what's the trade-off between interpretability and performance. So there's obviously a lot of techniques like using surrogate models, for example, or even getting approximate explanations. Consider those are important. Can your platform sort of show you? Look for those as you're making decisions over here. Similarly, there's obviously the multiplicity of good models, right? So again, goes back to the no free lunch theorem. If there's a lot of different models, which ones do you pick? So the same objective metrics, can you pick a model which is simpler to understand and more interpretable, but at the same time gives you performance which is similar to or close enough to the best model out there, right? That's important. Fairness and social aspects, these are becoming more and more critical. So especially ML models are becoming very prevalent in things like credit scoring, for example, or even healthcare use cases. It's critical to evaluate if that the model doesn't bring in human bias in or build discriminatory models that can discriminate on the basis of gender, age, ethnicity, etc. Right? So how do you do that? So you want techniques that can help identify disparate impact and help remediate it, right? So find tools that can help you do that and see if your platform supports that. Trust is of course critical. So you want a whole bunch of sort of model debugging tools. So think about ways to debug the models. There's obviously the classic techniques, data mining techniques like PDP, variable importances, Shapley, etc. But going beyond that, what other techniques are available to help debug the model and understand how well it's performing in real world, right? So giving that level of granularity in the predictions on each individual prediction is important. finally, the last two pieces are security and hacking. So this is a very, very new topic, and I highly recommend watching the webinar that we did by Patrick Hall, who has a full webinar on this topic. But there's a blog as well. But can you use these techniques to understand if if your model is vulnerable to certain sort of regions of the space, right? So can your model be hacked by some inputs which are designed to fool the model, right? So how do you do that? So like finding using different techniques to identify those things and solve for those, building adversarial models, adversarial data sets to actually tune your, like find those weak spots for your model. So think about those considerations as well, especially when you're using AutoML, because you don't know what actually went into it. You may not know fully. And then regulatory and control environments, this becomes very critical. This is something that we tackle all the time. Some of the largest banks, healthcare companies, insurance companies use our models in production. So there are legal requirements to be able to explain every single prediction. For example, if you deny credit to someone, you have to explain exactly why that happened, why the decision is made. Similarly, if you are going to make a decision on an insurance payout or denying a claim, you got to explain as well. So fairness and a bias sort of reduction are important as considerations as well. So think about all these things when you're making a decision on what platform to buy. Ask these questions of your vendor. And obviously, you know, we at H2O are very focused on these things. That's why we're talking about this. But we truly believe that this is important for the space. So as an enterprise, and oftentimes we are in front of customers who ask us these questions, we tell the same thing. With that, I think we are at the end of the deck, but I know we ran out of time. We probably don't have any time for Q&A, but I recommend posting the questions. We'll try to get back with answers on those. I want to thank Boyan here for jumping in last minute for this webinar, gave a really wonderful overview on the space of AutoML. We hope that this was fruitful and productive and informative. The presentation will basically want to thank everyone who joined us today, and we'll send the slides and recording over shortly. Thank you.